Even though we're humble atmospheric scientists without great software engineering backgrounds, we can come into a system like that and build a model that allows us to know the different pieces of observations and the goals and bring it all together in a way where now we can deliver a truly operational system.
Welcome to the Microsoft Academic Research Exchange. I'm Darcy Ogden. In this video, Forrest Cannon and Randy Chase join us to talk about their work using machine learning and AI to predict the weather.
Hi, my name is Randy Chase, and I'm a senior atmospheric scientist at Tomorrow.io.
And I'm Forrest Cannon. I'm Vice President of Data Science here at Tomorrow.io. We're excited to be with you today, and Randy's going to start off this presentation.
And today we'll be talking about building weather intelligence through novel observations, AI, and the cloud. So for those who don't know much about Tomorrow.io, we're a somewhat small startup company that started back in 2016 in Boston, Massachusetts. And we're a weather tech company that provides intelligence to a broad spectrum of customers across the government, as well as across the industry sectors. Our general mission here is to help every business and government implement high-impact weather resilient systems to manage their challenges and opportunities. We do a lot of this weather intelligence and providing that weather intelligence data to companies through three main groupings at our company. This first part, or the first grouping, is this proprietary data part, where we're collecting high revisit microwave scans of the Earth. Those proprietary data then flow into AI-powered modeling systems that provide insights on things like precipitation, wind gusts, temperature, anything that a company could potentially need. And then finally, those AI-powered modeling systems feed our customers through an online resilience platform where they can use agentic AI to query specific questions about maybe their logistics or any sort of thing that they care about. We'll start here by talking about the proprietary data that we collect globally. Specifically, we're doing this with something called the Tomorrow.io microwave sounder. This is a small, you can think about it like two cereal boxes that are stacked on top of each other. So it's a CubeSat. And on this CubeSat, we have this small spinning piece called the payload, which takes takes pictures from orbit in the microwave spectrum. Specifically, we're taking pictures around the 91 gigahertz to 204 gigahertz, and this allows us to retrieve information like temperature and humidity across the globe through the 3D atmosphere. You might be wondering, why do we collect specifically microwave data, and why is that important for weather forecasting? And if you don't know much about weather forecasting, or maybe you haven't heard about this before, but weather forecasting is actually an initial value problem. So that means in order to forecast the weather, we need to know the current state of the atmosphere. So to build this 3D numerical reconstruction of the atmosphere, we take things like, a lot of people are familiar with thermometers. We take our thermometers on the ground. We take measurements from airplanes that profile the atmosphere. Maybe you've seen a weather balloon. We launch these weather balloons that take profiles of temperature and humidity. And then we also take things like satellites, including our own, to build this high-resolution 3D reconstruction of things like temperature, humidity, wind, pressure, clouds, everything you could think of, a full dynamical 3D twin of the Earth's atmosphere. From there, we can take that 3D representation of the atmosphere and evolve it forward in time, either through our knowledge of physics, things like the Navier-Stokes equations, or you can do a much more quick version of that weather forecasting more recently with AI and machine learning. So you can evolve how that weather would move through time. So the example that's being shown here is a cyclone and how that cyclone moves through time away from the current time. So everything in weather forecasting is very sensitive to the original 3D reconstruction of the atmosphere, because we are not perfectly able to characterize the full state of the atmosphere at any time. So if you have slight changes in that initial condition, you can see here that we have multiple trajectories of the evolution of the atmospheric state. And that's why when we talk about proprietary satellite data, informing the atmospheric state with more and more observations is generally thought to improve that representation, which then will improve the downstream weather forecast. You might have had a similar question of why microwave as opposed to, say, infrared, or maybe even just visible imagery that you and I can see with our eyes. And the reason for that is primarily because of clouds and precipitation. So you could see here, this is a nice graphic from the UMetSat, our friends across the ocean. And you could see that there are lots of clouds and precipitation at any given time that are ongoing during our everyday lives. And when you try to retrieve things like temperature and humidity, and not just the surface temperature and humidity, maybe the full 3D atmospheric profile, those clouds and precipitation actually get in the way of retrieving information. So in the microwave, if you don't know much about scattering theory with the clouds and precipitation, in the microwaves that we specifically take pictures at are less sensitive to small cloud droplets and ice crystals. And so the example here on the right, you can see it's flipping between our microwave imagery and something called GOES-19, which is our operational, the US government's operational weather satellite is an infrared image. And you could see around these thunderstorms down in South America, you could see that there's a lot more clouds that are being shown up in the infrared as opposed to the microwave. And what this enables the microwave to do is you could essentially see through those clouds and still sense the temperature and humidity profile underneath. Where if you had it with infrared, you wouldn't be able to see anything underneath that cloud layer initially. So at Tomorrow.io, we've been specifically targeting these microwave wavelengths to take the measurements globally. And another reason why we're specifically targeting, besides this idea of being able to sense in more places where there are clouds and precipitation, are that there are large gaps in our current observing fleet. And I mean our as in like the weather community. So you can see here on the right, this is an animation of all of the government available microwave sensors, things like ATMS, MHS, GMI, SSMIS. Maybe you've heard of some of those acronyms, but it's the whole government global fleet of microwave imagery that anyone could go get access to at any given time. But you could see that there are large gaps in time of where these satellites are taking measurements. These are because they're in low Earth orbit and they process around the globe, and it takes about 90 minutes for each orbit for these satellites. So you can see there are large gaps, and one thing we were trying to fill with our specific Tomorrow microwave radiometer is to fill a lot of these gaps in time to provide another constraint to our numerical weather prediction. So as of today, we still have 11 satellites on orbit, and we're planning to launch more this year and next year to keep this high revisit of microwave information coming down from space, specifically from Tomorrow. So the bottom right now includes our satellites on top of the government fleet. And if you take an average of all of those satellites and how quickly you're getting a new image that can then be incorporated into weather forecast, on average, we are reaching an hourly global revisit rate. And you'll see that there are some spots where we get that global revisit rate around an hour, which is shown here by this line plot on the right. Some places we do better than an hour, some places we do worse than an hour, and these are all parts of the dance that we have to do with low Earth orbit satellites and putting them in different inclinations to maximize our coverage of the planet.
Thanks. And Randy's done a real nice job of sort of setting the scene, what we're trying to observe and why. And now I want to kind of reframe us a little bit on how it actually benefits our customers to have this kind of information. So as we noted in the introduction, like our end goal is to be able to provide weather intelligence that helps our customers from enterprise to government to really be able to make better decisions with respect to what the weather is going to do. Under the hood, that's driven by models, of course, and those models are driven by the observations that Randy has noted. So just to reframe this and to look at this in a little bit more tangible way, on the next slide, just have a nice image of a shelf cloud. This is a really strong thunderstorm. I think just looking at the image, you can kind of get a sense of what that might have felt like in the moment where right before this thing starts to drive really intense precipitation rates. There's maybe a cooling, a downdraft, sort of a chill in the air. And I like this picture because it's interesting. It's in Panama City, and it's an area that doesn't have a lot of observations. It's an area that doesn't have a lot of very high resolution weather information like we might benefit from here in the United States. And so it begs a lot of questions about how would we actually make a good forecast of this? How would we observe that this system had developed and what it was going to do next? And I think that really drives a lot of the motivation in how we build. We take something like that shelf cloud and we think, well, if there's not really a radar, what observations do we have? We can see from some of those other images that Randy had shown where we had the geostationary satellites, and you get those nice cloud bands moving across the atmosphere like you might see from many space-based images. We also have our microwave sounders, which Randy's noted have the ability to maybe see through clouds a little bit more. So when we think of that image on the previous slide where we had that shelf cloud, that strong precipitation event, a storm system brewing, how are we actually going to predict that? And the way that we do that is by taking information sources from many different satellites, and we pool that information, whether it's from geostationary satellites that see a broad picture of cloud tops, for example, or our sounders, which Randy noted can see through clouds and are sensitive to different characteristics in the atmosphere. We bring in things like topography and many different auxiliary sources, and we train these models to then predict observations where we do have radars. There are certain parts of the globe where we have very good spatial observation of precipitation. And so we build out these nice neural networks that can learn this relationship between a very diverse set of observations that are globally available and the very localized, high resolution, very good observations of precipitation from radar. And so we'll build out these large models, these emulators that take all the different patch data set, learn a relationship, and then an inference can run forward. And I've got a nice image here of just some of the software that we use on Microsoft Azure ML. This is a nice example where we've gotten our training data set in really good shape, and we're really trying to optimize the GPU usage here, making sure that we have tiles of a certain size and all the other trade-offs and decisions that are made. And one key point here is Randy and I are trained atmospheric scientists. We're not software engineers. So we're really looking to the broader community, things like open source tools that we pick up from NVIDIA's PhysicsNeMo repository and Microsoft's Azure ML training capabilities that allow folks like us who want to spend more of our time thinking about how to really make the atmospheric prediction as good as possible to focus on that and have very good tooling next to us to augment our abilities to do that. And so on the following slide, you can kind of see how this comes together. As I was mentioning, we have on the left certain areas of the globe where we have very good radar imagery. And so this is Hurricane Helene coming across the southeast US a few years ago, very impactful storm. On the left-hand side, that gray shading is where we have radar coverage. And you can see as the storm makes landfall that it kind of goes from nothing over the ocean here in this loop, and then you start to see it kind of evolve and come on shore. And so what we're trying to do in that neural network is really build a system that can take advantage of the geostationary satellite information and the tomorrow microwave sounders, which are seeing global pictures of everything, train those algorithms to use that information to then create a radar type image that exists well away from radar. So that storm system that we saw in the previous image with Panama City, for example, an area where you don't have radar coverage, now you can generate a weather prediction, a retrieval of precipitation in the area that very much looks and quantifiably scores like precipitation from a radar, but in the absence of that radar. And so this really helps us if we think on the next slide, how do we actually deliver value through customers? Not only have we demonstrated that we have this constellation of global observations that are really helping us get a better picture of what the atmosphere is currently doing, where storms are, how intense precipitation is. But you can see we have the tools through Microsoft Azure ML to really train models. Even though we're humble atmospheric scientists without great software engineering backgrounds, we can come into a system like that and build a model that allows us to know the different pieces of observations and the goals and bring it all together in a way where now we can deliver a truly operational system. And this is just an image here on the left of the platform that our customers would see, which is a globally complete spatial precipitation map, right? It's meant to be not only the real-time best estimate of where it's raining in the world and how intense, but that's used to then drive the predictions forward from in both nowcasting and short-range forecasting approaches. And so that kind of brings us to the next slide, which is not only have we had success in precipitation, but we're starting to see these capabilities really impact our full suite of atmospheric modeling.
And this is something we're building internally, is a way to incorporate our new proprietary satellite data specifically into global weather forecasts. So the example Forrest was showing before was primarily just precipitation, but there's obviously a lot of use cases for knowing the full 3D atmospheric state, things like temperature and humidity, wind speed again. So something we've been building, we're calling the initial condition generator, or ICGen, which is a data-driven method to combine traditional numerical weather prediction, say the forecast from NOAA or maybe ECMWF, and blend those together with our novel satellite observations. So that's what I'm showing here on the slide. As you can see, our background state, which is the old GFS forecast or an IFS forecast from NOAA or ECMWF, and we combine that with some recent observations from our satellite data. We then use ICGen to blend those two together into a better estimate of the current weather state, from where we take that initial weather state and combine it with Microsoft's Aurora weather forecast model to then give us a full 120-hour or 5-day forecast of the 3D atmospheric state going forward. So early versions of this model are showing some promising results. And here are some animations of our real-time running pipeline using ICGen with Microsoft Aurora. And this is specifically so far leading to some skillful 5-day forecasts that are improving with our satellite. And you can see some examples here on the right. The reds and blues are showing how the satellite changes to that initial weather state are changing things like front locations or the intensity of cyclones as they start to evolve on the atmosphere here.
And hopefully from these various different examples of the types of models we run, you can start to appreciate how we're taking not just the models themselves to drive predictions forward for our customers, but also thinking what are the things that we can do for our customer base to really improve upon the existing state of modeling. And the way that we've done that is to work in sort of this convergence zone between new capabilities and satellite constellations that are afforded through lower orbit, sort of micro and small sat constellations. And at the same time, the large capabilities that have impacted the field in machine learning based weather prediction, where we've seen great advances. So between the two of them, we're seeing a large ability to impact the skill of our forecast models and to bring that forward. The one thing that underpins a lot of this is, again, the Microsoft Azure stack that allows us not just to process the observations coming back from our satellites, but also to train and run the models in inference that deliver to our customers. And on the next slide, that's essential because not only is this a matter of building out those models, but we also have to maintain them in an operational setting, right? Through Azure Kubernetes services, we're managing the ability to really have, very consistent uptime that if we have customers that are dependent on weather information, whether it's an airline that has distributed assets across many different airports or a logistics enterprise customer who has a distributed rail network, what we really need to ensure is that we can always consistently deliver the information that they're relying on to make their business decisions. And that's underpinned by the compute infrastructure behind this. So in our final summary slide, hopefully you've gained a little bit of understanding of not just how Tomorrow.io as a company is looking to advance weather prediction, but to truly make that an operational benefit to our customers and the community through Microsoft Azure stack. And so not only are there a lot of advancements in the field that have benefited us as a company and Tomorrow.io being able to drive value for our customers, but it's also been an incredibly exciting time to just be a scientist, to see the amount of capabilities that have happened in being able to observe the weather through the benefits of small sats and constellations that have become affordable to a broader community, as well as to see the advances in the community in machine learning-based weather prediction. It's not just our company, but a very broad swath of the industry making great strides at this, and to be able to work at the interface between academia, government, and industry to really drive a lot of value within the community, and our ability to be able to predict the weather has just been incredible over recent years.
On behalf of Tomorrow.io, thanks for coming to our talk today, and hopefully you learned something new about the weather enterprise and how weather forecasting is done. Thanks.
Thank you, Forrest and Randy, and thank you for watching. Please be sure to check out more of our videos at the link below.